In this video we're learning to understand the vector product, which is also called the cross product. We'll be focusing on three-dimensional vectors. If you can master those, two-dimensional ones are very easy. So this is important because it's an important part of specialist maths, but it has a lot of applications which I'll go through soon. What I'm looking for is your ability to understand what a vector product is and contrast it with the scalar product, also how to use it mathematically. The scalar product, as we saw previously, produces a scalar quantity. So it starts with two or more vectors and a scalar is produced. It is also called the dot product because it uses a dot in its notation. However, with vector product, a vector is produced, a vector quantity. And it's also called the cross product because its symbol is a big X or an uppercase X. Applications of the vector product are seen when we're finding the volumes and areas of geometric shapes. Two and three-dimensional shapes can utilize the vector product. Also, in the physical world, things like angular momentum and torque, which are important physical properties and physical concepts, they use the vector product as well. But there are many other examples. Showing you the most direct way of finding the cross product or the vector product of two three-dimensional vectors is done using a process involving the determinant, which I'll explain in a minute. Before we do that, let's just define two generic vectors here. We have vector A, which is something I plus something j plus something k. So we use those A1, A2 and A sub 3 just to show there's not necessarily the same coefficients in front of I, j and k. And a second vector B, which is B sub 1 I, B sub 2 j and B sub 3 k. So they're just generic vectors. The determinant is something you'll study in specialist maths. It's usually taught with a matrix unit, and it's something you'll see in the future. But even if you don't fully understand what the determinant is for, you can simply follow this process I'm about to go through. And there are other ways of learning how to do the cross product, but this is the most direct way for the purposes we have in mind. Firstly, this array here, it's a 3 by 3 array, and it has, instead of braces, it's got vertical lines on it, so it is not a matrix, it is called the determinant of a matrix. And it's, as I said, it's just a rectangular array of basically characters and numbers. This one is a 3 by 3. So for two three-dimensional vectors, we need a 3 by 3 determinant. You always put I, j and k in the top row like that, and because they're in bold there, that means they're vector quantities. You can also put tildes underneath instead if you want to. On the second row of the determinant, we put in the coefficients of the first matrix, A1, A2 and A3 from above there. You can see them arranged in the second row. And then in the third row we do likewise of B1, B2 and B3 from the second vector B. To find the resultant of A cross B, we go through the determinant process. So we'll have three sets of values that we do various operations on. First thing you do is imagine if you put your finger on I, and then you also covered up everything that's in column I and also in I's row. We would have all of those covered up, and then we just focus on these terms here that are left over. Now these two terms here, A2 and B3, will go together, and A3 B3 and B2 will go together. Exactly how this works is written just down here. Down the bottom you can see that because we covered I up first, we write I. Now remember, that's a vector, that's a unit vector I, so either put a tilde or bold there. We write that down first and leave a space in front of it. In the space in front of it, you can see it's A2 times B3. That's because they're diagonally opposite. If you look in this first diagram here, you can see exactly what's happening. So A2 times B3 happens there, then it's minus, always minus, then the other pair A3 times B2, and we close the brackets. Don't try and evaluate that yet, just write it down. Now you notice that that was positive, or you might not have noticed, but it was positive. There's a positive 1 out the front. In other words, nothing changes. But you notice that this one's a minus. That's like having a minus 1 there. If you look a bit further along, the third one is back to positive again. Why is that? Let's have a look. In the future, when you study determinants properly, you'll know that they are given signed values, S-I-G-N-E-D, meaning positive and negative values. So it always goes starting with the top left, or position row 1, column 1. I will be positive, J will be given a negative sign, K will be positive, and it keeps going. Positive, negative, second row, negative, negative, and positive, negative, positive. In this work, it's only the first row of pluses and minuses that we need to worry about. Those other ones, the pluses and minuses below, are irrelevant at the moment for us. So you can see that I will take on a positive value, I being the value I with its coefficient on the front. J will have a negative 1 multiplied by the same type of calculation, so that's going to be minus there. And K will be back to positive, because you can see up here it has a positive sign to it, and that's why it works that way. Getting back to our calculation below, we've already discussed that part of the calculation. This one here, you could say it's added together with that negative 1 on the front, and that's that negative we saw just up here. That's what's really happening. Of course, when we add a negative quantity, we just have a minus. So we can just put back what was there. Okay, they're equivalent to each other. So we can see that once we've established that that's minus, the next part of the algorithm, J, so we write down J, so you do it once for I, once for J, and once for K. Cover up J, and cover up everything in its column, cover up everything in its row. And then you can see it's A1, B3, A3, B1. So we diagonally multiply that. Now notice the order, the red always becomes before the green. That's always the correct order. It cannot be reversed. Those reasons will be explained to you in the future when you learn about matrices and determinants later on. It won't be in this unit. So we see that's done in the same way. Likewise with K, if we have a look, up here we cover K and everything in its column and everything in its row, and we can see what's left over. Then down here we can see that this is what we do. We can see that that's the result. Let's have a look at a specific example. If we have to find the vector product or the cross product of vectors u and v given there, they're given in a storage vector type form, but we know that this first vector u would be the same as I plus minus 2j plus 4k. So it's easy to convert them, and the second vector v will be negative 2i plus 3j minus k, so as long as you remember that. So you may need to pause parts of this video to have a closer look. So you can see that we've basically got our I, j and k written down. We've got the first vector, u, written in its I, j and k columns. Vector v likewise. Remember, we start by covering up I, doing the cross multiplication, covering up j, cross multiplication, covering up k, and remember our signing. And you can see the process fully expanded in the second row here. Pause the video to have a closer look. Then numerically there, you can see we have positive, negative, and positive. Be careful of that. And we simplify what's in the brackets for I, then j, then k, and we get our result, which is a vector, negative 10i minus 7j minus k. Optionally, if the question needs you, you can write it in the other form, but don't do that unless you really need to. Time to try some cross products.